Hi everyone, and we are back at the Global AI Student Conference with our next speaker, Emre Kikiman from the Research Center of Microsoft. Hi Emre,
Hi, how are
welcome
you
to the
doing?
show.
We're doing
Thank you
good.
so
How
much for
about
having
you?
me.
Thank
Good,
you so
thanks.
much for joining us. Can you tell us a bit about yourself?
Of course. My name is Emre Kujaman. I'm a researcher at Microsoft Research, where I work on causal machine learning and its applications to decision making in particular.
This is amazing. So you may share your screen and you can start your presentation.
Sure. Great. So thanks, everyone. I'm really happy to be here. This is an exciting event, and I hope everyone's enjoying the presentation so far. So my talk is going to be about the foundations of causal inference, and I'll also talk a little bit about our open source causal analysis tools that make causal inference a little easier. So just a quick note, of course, this is work that we're doing together with many collaborators, both at Microsoft Research and in the broader community. So I'll thank them at the end. And right now I'll just dive into why causal inference. Once we talk about a little bit about what causal inference is and what it's good for, we'll go into 4 steps of causal inference to kind of make the process a little bit easier. And then I'll talk about our open source suite to help people get into and scaffold the best practices of causal inference. So first I want to say a little bit about, what are causal questions. So let's start by reviewing what is a causal question. So a causal question is focused on a cause and effect relationship, usually where we want to analyze or make some kind of change in the world, and we need to know what the effect of that change is going to be. For example, some of our partners want to know how their model and, sorry, so for example, we might want to know how an ad campaign affects user conversions. We might want to know how farming practices affect soil carbon sequestration. We might want to know who is going to benefit from a drug or not. So these are all decision-making tasks, asking something about the world and how it works in order to enable some kind of critical application. And these decision-making tasks, AI has had a tremendous success in capturing complex patterns and leveraging them for things like classification and generation. But oftentimes we find that decision-making and asking what-if questions is a little bit harder. And the reason is that machine learning success usually relies on something that's called the IID assumption. That is that the patterns that we see in our training data mean the same thing as the patterns that we see in our deployment data. And the problem here is that new decisions often change these patterns. So for example, when we apply machine learning to digit recognition, we find that this recognition accuracy drops to maybe 64% under rotations. Just very simple changes to the patterns in our data. This is the case where normally we would expect recognition to be around 99, 100%. Similarly, we see that object classifiers fail when we see 3D perspective shifts. For example, rotation of a stop sign might fool an algorithm into thinking that something is not a stop sign, but a dumbbell or a racket, something that's obvious to us as people. And studies have found that this occurs in more real-world settings with real-world data as well. In particular, a study of hundreds of chest scan COVID classifiers identified that instead of detecting COVID, these classifiers actually detected something else about the image. So for example, in one data set, a classifier was trained to identify the COVID versus non-COVID chest scans, but instead it identified whether people were sitting or lying down during the chest scan, because the people who were sicker tended to lie down. So that was a false kind of a spurious correlation that the classifier found it easier to pick up on rather than actual signs of illness. So How does causal AI help this situation? How does it help us break apart some of these spurious correlations and patterns and focus in on the patterns that really mean the same thing as opposed to the ones that might be changing? Causal AI helps by focusing machine learning models on a cause and effect relationship that, um, that are stable. For example, in this scenario, we see that we have some data here where we've captured some variables z and x and y, and we want to know what is going to happen if we make a change. What if we change this x1 value to from 20 to 100? What would be the output result here? Now we might think that, well, maybe the output result y comes from this variable here. So if we change it to 100, maybe y will be 100. But what if this y didn't take its value from x1, but took its value from something that happened earlier? This is z. Then what will y be? Will it be 20 still or 100? Clearly, our understanding of what's causing y to change over time is going to greatly influence what we believe is going to happen when we change x1. And so the way the causal AI helps here is it focuses on these cause and effect relationships that we believe are stable and independent. They're grounded in the real world, and these are going to be robust to kind of outside changes that we might be seeing in the system. We do this by getting some kind of systematic reasoning over domain knowledge. So we're going to bring our knowledge of what these potential causes might be, these arrows, into the system and use those arrows to guide our data modeling and the learning of the potential relationships among these features. In a way, you can think of this, if we want to get a little bit more mathematical for a second, we can think of this as being an observation over a joint distribution of these three variables, x, y, z, and that conventional machine learning just learns one joint distribution, that this is how the distribution of the world works across all these variables. And when this relation changes, say because we are switching a value of a variable from 20 to 100, this distribution is no longer going to match the new changed world. What causal AI does is it builds a model of a factorized distribution. So instead of just being one joint distribution of all these variables lumped together, we're seeing a little bit more structure here based on where we put these arrows. This factorizes this distribution into, say, multiple distributions, and we can pick, as we change z, what is the world going to look like. So I want to get into one maybe a little more specific example of why this is particularly important for decision making. And that's that decision making can, and that's just to illustrate how decision making itself can change the data distribution. Let's say we have a simple task in the agriculture domain. We're going to irrigate based on our predicted soil moisture levels. We're going to train our models of predicting soil moisture levels on years of sensor data from real fields. And we're going to ask the question now. Now we're ready to deploy, we're out in the world, and we're going to say, okay, it's going to be really hot in 2 days. What do I need to do to water? Do I need to water my fields? Is the soil going to be dry or sufficiently moist on these really hot days? The model is going to say no. We don't have to water. The soil moisture is going to be very high. And this doesn't make that much sense. It's really hot weather. Wouldn't we think that the soil is going to dry out? Well, the problem is that the models are only predicting high moisture because the farmers in the past have always watered on the hottest days. So in a sense, we have this relationship here where we're asking a question about, what is the effect, what is soil moisture going to be based on hot weather? And we're ignoring in our model the influence of our irrigation decisions or our irrigation policy. Once we decide to change this irrigation policy, we're also affecting the model of how hot weather affects the pattern between hot weather and soil moisture as well. And that means that our decision making based on this model is going to fail if we don't take that into account in the first place. So how do we take that into account? I'm going to go through the 4 key steps of causal inference. We are going to first model to create an encoding of our assumptions, those arrows that I mentioned before. Then we're going to go through a step of identification. This is about formulating what we need to estimate. And then we're going to go ahead and compute that statistical estimate, and then we're going to double check our assumptions. And that last step in particular, I'm going to highlight as being very important. So modeling our assumptions. This is about taking our knowledge about how the system, about how whatever it is that we're modeling, the system, the world works, and then converting this into something a little bit more formal that we can reason about. A good model exposes the key causal relationships between the variables that we are observing and capturing and other variables in the system, including the one that we're trying to ask a question about, the kind of what we're going to be changing as part of our decision. The model is capturing the assumptions about how these variables affect each other, and in particular, it's affecting. We're capturing the direction of the influence. We don't need to specify all the causal relationships, but really the more complete, the better. And sorry, we don't need to specify all the causal relationships. I should highlight that we do need to capture the relationships between the features we're observing. If there are features that are exogenous to the system, we can play around with how we define our system in order to compensate when we don't have full knowledge of things. And if we ever aren't sure about a relationship, we can add an arrow just in case. The arrow means that there might be a relationship. So we don't have to know for sure, but we do have to encode when we are unsure. So the edges encode, in this case, here's an example of 4 features that we've been observing, A, B, C, and D. And the edges, these arrows encode potential mechanisms where, we think A might influence B, we think C might influence B, and we think B might influence D. A key assumption here is that the missing edges don't exist. So there is no way for D to change C, for example. And from a formal point of view, what this graph is encoding is that there's a statistical independence, that if we know B, we can predict D without knowing A or C, for example. D doesn't depend on A or C except through its influence through B. Now, the key intuitions here, as I said, is that the assumptions are encoded by the missing edges and the direction of the edges, that these relationships represent stable and independent mechanisms. That is, as other things outside in the world change, these arrows are not likely to change. And that's what gives us some more trust in the robustness of these models when we're going in and changing our decision-making policies, and et cetera. This graph, interestingly, can't be learned from data alone. It's something we have to bring from outside the data set itself in the form of domain knowledge. We can learn the graph to some degree, but in the end, for any given data distribution, there's going to be a set of graphs that all can possibly explain that data, and it's our domain knowledge that will help us choose which one of those graphs is the right one. And it's important to note that graphs are a tool to help us reason about a specific problem. When we ask a different question, we might need to bring in different information that wasn't relevant before. So, for example, one graph might be looking at the effect of user fatigue on our observations of people, say, their outcomes from their usage of an online website, for example. So we might have something we control on this website that affects what they do. So this might be whether I use a feature in Office, or do I, what am I clicking for on search engines, or what am I buying on an e-commerce site, for example. Whether or not, or what my interests are and what I've done in the past is going to influence what I do now, and is going to influence whether or not I see a particular opportunity, maybe on the website. Maybe this is what leads me to a particular product, and then I'm going to decide now whether I purchase that product or not. And maybe my purchase of that product is also going to be influenced by how tired I am, for example. Now, here this encodes several assumptions here that user fatigue, for example, doesn't change what I'm interested in. Past clicks don't directly affect the outcome, for example, and we can keep reading off what these arrows mean or don't mean. Now, when we're asking a question about what is the effect of this treatment, this variable that we control, maybe whether we're highlighting a particular opportunity, whether we're putting a message in front of the user to tell them about a new feature that was released or something. What is the effect of that going to be? Well, when we look at our data, we can see that because of these multiple arrows that are influencing both whether someone sees this message or so, and this outcome here, we're going to have to disentangle the influence of for example, the user's past interests and its influence on the outcome from the influence of this message or this treatment itself. So this is going to be represented by a new graph that we want. It's basically we want to compute. Basically, we get to see the data generated by this graph from our real world data, but we want to answer questions about data that would be generated by this intervention where this treatment is completely independent and disentangled from everything else. So identification is about figuring out how we can take this question where we have a clean kind of signal about the effect of treatment and why without any influence from anything else in the graph. And we want to figure out how to calculate this from the data we can observe on the left-hand side. Now, one way to do this is through a randomized experiment. Often we run a randomized experiment where we flip a coin. That coin flip that decides whether or not to show treatment to someone independent of everything else is essentially generating this interventional graph here by construction. And so in this case, we can directly read off how this treatment affects the outcome that we care about directly from the data we observe from the randomized experiment. But if we don't have this ability to run an experiment, then we have to start to identify how to disentangle those other variables. There's several different approaches to identification, and we're not going to go into the technical details of them here, but they are implemented in the tools that I'll talk about at the end. So the third step, once we know what we want to identify, once we have the statistical expression that we're going to compute, then we start to look at how we're going to compute that from the data we have right now. A common way to estimate the effect of a particular treatment is to match data points that have the same kind of background variables that we think are entangled up in our observations, and match them up and compare their outcomes. So for example, let's say we have a data set where there's a number of people in our control group who haven't been exercising and a number of people in our treatment group who have been exercising, in this case, like bicycling. The question now is, well, what's the effect of bicycling on some outcome that we care about? Maybe it's some health measurement, blood pressure or something else, cholesterol. And what we're going to do is we're going to find pairs of people who are identical, very similar, according to some metric, and except for one difference, and that one difference is going to be whether the people are biking or not. So you can see we've lined up our population here, and they're all exactly the same, except for the fact that on the right-hand side, we have a bicyclist, and on the left-hand side, we don't. Now, once we see this now, we can, this is like now, this subset of the data is like a randomized experiment. If we look at any particular attribute of these units, we're going to see that the people who exercised and didn't exercise are exactly the same. There's no entanglement or influence on whether people are biking or not in this data. There's going to be some people that we weren't able to match up, and then that's going to basically limit, who we're talking about when we talk about the effect of the bicycle. But otherwise, for this part of the population on top, we're going to be able to correctly identify the influence of the bicycle on the outcome that we care about. Now, what identification gave us was the list of the attributes that we need to do the matching on. So, for example, in this case, age is one of those attributes. Maybe whether someone is wearing a hat is another one of those attributes. Now, matching is one particular algorithm, but we do have a lot of challenges here around how we handle variance and bias and how we trade off some of these issues. For example, what do we do if there's many people who look very similar on one side of the data and less people on the other side? Then we might have issues that we have to resolve. There's many different machine learning based methods that help with this and take us beyond simple matching approaches to more complicated approaches. And these methods are also in our open source library as well. Now, once we have analyzed this data and we've gotten our estimate of a result, we have to make sure that we trust it. And how do we do that? In machine learning methods, conventional correlational machine learning methods, we often get to test our analysis against a outcome that we already know. We have some holdout data that's been labeled, and we get to do something like cross-validation to give us a very kind of quantitative measure of whether our analysis is working or not. The challenge in causal inference is that we're asking a question about something that we don't always get to observe. So, for example, when we were changing our values before from 20 to 100, we don't actually necessarily get to make that change beforehand and see what the value is. If we do get to change it, we don't know what else might be affecting that. Maybe that value. So if we make the change to 100, then we get to see the outcome, but we don't know what would have happened if we kept the value at 20. So robustness checking becomes a little bit more difficult here. In particular, our estimate now depends on many assumptions of our algorithm. We have to validate that, ask ourselves during the modeling step, did we miss any unobserved variables that we should have matched on, for example? During identification, we might wonder whether our identification algorithm made some sort of parametric assumptions about what the data looks like. Or our estimation step, do we make assumptions that might lead to higher variance than we would desire? And now again here, the goal is to gain trust in our analysis results. And so we recommend running a number of different tests on our assumptions to try to validate them if possible. That's rarely doable. To refute them, to try and prove them false otherwise. And if we can't prove them false, then that helps us a little bit. And then finally, to run a sensitivity analysis to ask ourselves about how wrong we would be if our assumption is a little bit wrong or a lot wrong. And then we can use our domain knowledge to understand how much we believe our assumptions and what the impact of it on our final result would be. So those are the 4 steps: modeling, identification, estimation, and then robustness checks, validation and refutation, that is. Now, to help people through this process, it can be it can be very different in some scenarios from conventional machine learning, especially in that validation, refutation, and the encoding of our assumptions. We have built out an open source suite of tools for causal AI. This consists of 4 libraries that we have out in the open source community. The first is DoWhy, which is built for scaffolding the best practices in causal analysis end to end. EconML, which really focuses on the sophisticated estimation methods that bring in the latest in machine learning for causal inference. Causica is a library that uses deep learning methods for causal discovery. This is about trying to get as close as we can to that first causal graph from modeling assumptions from data, kind of like a bootstrapping based on a different set of assumptions. And finally, the three libraries here, DoWhy, EconML, and Causal, are all Python libraries. We've put on top of these tools a ShowWhy for no-code interactive usage by data analysts who maybe aren't coders, for example, or for data scientists who can code but want to quickly explore these results. I'm not going to go into too much detail here with a coding example, but I did want to just highlight how straightforward the APIs are. So the first the first thing we do here might be causal discovery, where we load in our data, provide some domain knowledge, what we're already willing to say about constraints that we want to put on this graph. For example, we know that there's certain edges that are connecting our data already. Then we want to discover the rest of it. Once we have that discovered graph, we're going to run that's now our modeling step. The next thing we're going to do is identification. So given that we want to identify the effect of providing technical support on revenue, then we're going to come through and we're going to say, identify the effect and tell me what I need to estimate here. Once we have that estimand, we're going to feed it into our estimate effect function, and we're going to let the library know which method name we want to use, what statistical estimator we want to use. And after that, we're going to go through and call our refutation functions, our sensitivity analyses, iterate through all the different methods that are available, and look at the results to see if they're holding up to our tests. And then overall over this set of Python functions, we can use our interactive no-code tools that support causal discovery and exploration, that look at effect inference, the four-step process that we went through in detail, or a different approach to effect inference in the context of policy changes over time. So, for example, a law passing or something that affects many people at once. Now, our tools are pretty popular. They're open source, and we're seeing a broad academic and industrial usage. We're expanding these tools to incorporate new causal tasks, in addition to expanding them with stronger no-code and user interfaces as well. At this point, I think I have a few minutes left. I'll stop for questions and say thank you to the whole team in our collaborations.
Emery, and yes, we do have a couple of questions for you. First of all, thank you so much for your amazing presentation. And my very first question for you is it up to humans to identify like irregularities or assumptions, or can the AI identify the irregularity on its own to make itself more robust?
So some of the assumptions a human has to bring to the table. So our core domain knowledge, for example, that graph, at least parts of that are going to have to come from a person. But when we talk about the assumptions that are made about, like, I think I mentioned things like, what are the parametric assumptions that our identification algorithm makes? Those are things that come along with the algorithm. We know that a particular method makes a particular assumption about the shape of the data. And then that implies that we should run a check of some kind on that. Yeah, so we can track what assumptions you need to run based on the analysis that you're doing.
Awesome. I think we have time for one more question. And I know you're talking about causal AI, it's currently, you can do it in Python, and there's also no code solutions. Are there any other languages you can use with causal AI?
Yes. So we don't have libraries to support it, but there is a lot of functionality in R for these analyses as well.
Awesome. That is super cool, Emery. Thank you so much for coming on to the Global AI Student Conference today. I hope you have a fantastic rest of your day. Thank you so much.
Thank you for having me. It was great.
And now we get to pivot to an extremely exciting stream because we have one of our guest speakers in the studio with us. So I'd love to introduce you to our next talk, which is Smart Parking in Modern Cities, Challenges and Solutions. And we'll introduce Vadim